So today we're going to talk about improper integrals, and namely part A of improper integrals, in which we explore what happens when either the upper, lower limit of integration has an infinity in it, or sometimes both the lower and upper bounds of the integrals have negative infinity and infinity. These cases appear down below in the box. I just want to point that out to you and highlight. So in that box, it has three scenarios. One in which you have an upper limit of integration being infinity for number one. Number two, you see a lower limit of integration being negative infinity. And number three, you have both the lower and the upper being negative infinity and infinity. And so the conceptual idea behind this is, if we take a look at the graph that you see on the first page of your Chapter 7 notes, you'll see that you have a curve, specifically 1 over x squared. And the question becomes, does the area underneath that curve, between the curve and the x-axis, exist if we let one of the bounds go to infinity? So if we're taking a look at the area if we look at the integral, which represents area between curve and x-axis, and the bounds are 1 and the right-hand bound is infinity, the idea is this area does, and this is the new word, converge to a finite value if this curve y equals 1 over x squared grows closer and closer to the x-axis fast enough such that the area does eventually approach a finite value. Now, if we find that this curve doesn't get close enough to the x-axis fast enough, then we would get an infinite area, and therefore we would say that the area diverges and that it does not exist. And so we're going to take a look at the scenario in the sense that an improper integral, one of the limits of integration being infinity and negative infinity, and those ideas being concepts of really large numbers and not actual numbers, means that we're going to have to approach it from a limit standpoint. So each improper integral that we have, I'm going to zoom in right here, each improper integral that we have is going to be rewritten as a limit problem where we let the limit approach that, and I'll call it problem area, and the problem area being the infinity. We let it approach infinity. And then what we do is we evaluate that integral, finding an antiderivative, and then we apply the limit to it. And so each problem might have it will have an antiderivative tied to it, it will have a limit tied to it, and it might have a derivative because we have to apply L'Hopital's rule at the limit step. So you can see it becomes increasingly important that we remember all the concepts from first semester as we go through these problems. So let's take a look at the problem down below, example 1. So we're going to skip example 1 for now, and then come back to that in the next class and take a look at example 2. Okay, with example 2, you have what is the integral from 1 to infinity of e to the negative x. So this is very easy to spot that this is improper because of the fact that your upper limit of integration is infinity. So in fact, what I'll do is I'll highlight that. So infinity, that's going to be our problem area, and that's what we're going to have to replace. So the variable that's commonly used is b. So we're going to say let b approach infinity, and we're going to replace our upper limit of integration with b, e to the negative x dx. So if we think of this similar to when you were doing, let's say, a problem with parentheses in it, you're going to view this first as a antiderivative integral problem before you view it as a limit problem. So you just kind of, the limit, we'll let it hang out for a bit. We'll do this part first. So this is step 1. And then we'll do the limit part second. Okay, so let's go ahead and do the antiderivative first. So if we take the antiderivative of e to the negative x, it would be itself. And then we want to make sure we multiply by the reciprocal of what the derivative of the inside function would have been. So in this case, if I were to take the derivative of this, I'd also have to remember to take the derivative of negative x, which is negative 1. Therefore, in taking an antiderivative, we have to multiply by the reciprocal of -1, which is still itself. So negative e to the negative x is the antiderivative of e to the negative x. And then our limits of integration are 1 and b. The limit part is still on the outside, just kind of keep that on the outside. We haven't done anything with that yet. And then evaluate fundamental theorem of calculus, plug the b in, plug the 1 in. So what I'd like you guys to do after you plug the b in, make sure you subtract the negative, so therefore it's a positive e to the -1. Okay, at this step, I would like you guys, until you get comfortable with the limit portion of it, I'd like you to rewrite this step so that you don't have negative exponents. So here I would keep negative on that negative on the outside, 1 over e to the b power plus 1 over e. And then at that point, evaluate the limit. And here's why that's important. When I plug infinity in, if I'm not too familiar with the concept at first, if I plug infinity in to this step right here without putting it under a fraction or rewriting the negative exponent as a fractional term, then I might consider that going to infinity means that that is infinity. However, putting e to the b underneath your fraction now becomes you have a really large number on the bottom. If we have a really large number on the bottom, then that really means that the limit for that expression goes to 0. So here I'm going to just draw a line through it, and then keep in mind that this becomes 0 as b goes unbounded to infinity. And so I'm left with my answer being a finite value of 1 over e. And so 1 over e is, we would say, area converges, the integral does exist, and the area is 1 over e. Okay, let's go ahead and take a look at the next example. On the next example, same process, so I'm going to have you try to work through this on your own and setting it up. Okay, problem area is the infinity. If you want, go ahead and hit pause. I'm going to go ahead and start on the solution for this. So limit as b approaches infinity of 0 to b e to the negative x dx. I'm going to stop and pause and just say that it's important that you get yourself used to setting up the improper integral with the formal notation of the limit and the integral and replacing the b with infinity. I know one of the things I keep working with students on in this chapter is remembering to do that, because oftentimes what we try to do is just skip this step and apply the concept but not write it out formally. It's important just so that we get familiar with the proper notation for if it does appear on the free response, it would be expected that you write the limit with the integral. So at this point, we're going to integrate. Remember, we always do the integration first. So do that first, and then we apply the limit second. So once again, negative e to the negative x is the antiderivative. We're going to plug in our limits of integration. So negative e to the negative b, and then minus a negative, so plus e to the negative 0. If you didn't write it as a fraction in that step, go ahead and rewrite this as negative 1 over e to the b, and then plus e to the negative 0 is just 1, so plus a 1. And at this point, once that's complete, we're going to let b go to infinity. And when we let b go to infinity, we see that the bottom of the first term grows really large. This goes out to 0. And our final answer is finite, with it being equal to 1. So once again, the area converges to 1. Okay, the last example we're going to work on today is going to be example number 3. So example number 3, we see our problem area is the infinity. We're going to rewrite our integral so that it's limit as b approaches this problem area of infinity, and go from 0 to b of 1 over x squared plus 1. So take a moment and think about, well, what is it that if I took the antiderivative of 1 over x squared, I get this function? What function, when I take the derivative of that function, gets me 1 over x squared plus 1? Now this is going to be one that will become more and more frequently used in this chapter and in the series chapter. So if you can go back on your rules and take a look at that again if it doesn't look familiar to you, that is the arctangent. So 1 over x squared plus 1, that's the derivative of arctangent is that. So we say arctangent of x, its derivative is 1 over x squared plus 1. So therefore the antiderivative of 1 over x squared plus 1 is arctangent of x. And let's, again, apply all of the integration part first, and then apply the limit. So if we plug the b in, we have arctangent of b minus arctangent of 0, limit as b goes to infinity. And so if you don't remember what the arctangent graph looks like, the arctangent is the inverse of the tangent. So if you remember the tangent function going from negative pi over 2 to pi over 2. So first, let me graph. This is the vertical asymptote for tangent, pi over 2. So when we find an inverse, all the x's and y's are switched, and we replot that. So if we were to graph the arctangent using that idea, the arctangent graph has instead of a vertical asymptote, it has a horizontal asymptote, which I'll make as a dotted line. This becomes pi over 2. Down below here, this is negative pi over 2. And the graph, all the x coordinates and y coordinates swap, and it looks like this, kind of a sideways looking tangent function. And so when I go back to this limit question, the arctangent graph is over on the right. And the question is, what is the arctangent when you let b go to infinity? So as b goes to infinity, it's going to approach a value of pi over 2. Arctangent of 0 is 0. So my answer is a finite value of pi over 2.